You've probably heard of gradient descent, right? It's kind of the secret weapon behind so much of modern machine learning, doing everything from training massive neural networks to predicting stock prices. But how in the world does it actually work? How does it find the best possible answer? Well, today, we're going to crack that code together. Let's dive in.
So here's our game plan. We're going to tackle this in 5 parts. First, we'll look at the main formula we need to solve. Then we'll investigate the 2 big clues hidden inside it, how it finds the right direction and how it chooses the right step size. After that, we'll get into something I call the Goldilocks problem, and we'll wrap up with the absolute coolest part, how this thing basically runs on autopilot to find the solution.
All right, let's jump right in. Section 1, the algorithm itself. I'm about to throw the big and, yeah, maybe scary-looking formula up on the screen. Now, don't freak out. It might look like hieroglyphics at first, but I promise, by the time we're done, you'll understand every single piece of it. Okay, there it is. The infamous gradient descent update rule. You know, the best way to think about this whole thing is as one super simple instruction. Take a step downhill. That's it. And really, all the magic in this formula boils down to just 2 key ingredients, the learning rate and the derivative. So if we want to crack this code, we just need to figure out these 2 pieces of the puzzle. On the left, we have alpha, the learning rate. That tells us how big of a step to take. And on the right, you have the derivative, which tells us which way to go. Simple as that. So let's start with direction. Where are we going?
And that brings us perfectly to our first clue, finding the direction. I mean, how does the algorithm know which way is downhill? Well, that is the job of the derivative.
So what is a derivative, really? Don't let the fancy name scare you. It's literally just the slope of the function right where we're standing. Imagine you're on a curvy hillside, and you put a tiny flat board down at your feet. The tilt of that board? That's your derivative.
And this is just a perfect illustration of how it works. Take a look at the top graph. We're on the right side of that valley, right? The slope is positive. So our formula subtracts that positive value, and boom, we move left, downhill. Now look at the bottom graph. We're on the left side, so the slope is negative. And what happens when you subtract a negative number? Well, you're actually adding. So we take a step to the right, and again, downhill. It's genius. No matter where we are, the derivative always points us toward the minimum.
Okay, so we've got our direction figured out. Now for the second clue in our puzzle, choosing the step size. We know which way to go, but how big of a step should we take? This is where our good friend, the learning rate alpha, comes into play.
Alpha is really just a number, a positive number that we get to pick. It's like the volume knob for our steps. You multiply it by the derivative, and that controls how big of a leap we take. A tiny alpha means we're taking cautious little baby steps. A big alpha means we're taking a huge, confident jump.
And right away, this creates what everyone calls the Goldilocks problem. It's a classic. Your step size can't be too big, it can't be too small, it has to be just right. So let's see what happens when it's not.
Yeah, this visual says it all. Look at the top image. If your alpha is too small, you're taking these teeny tiny steps. Sure, you'll probably get to the bottom eventually, but it's going to take forever. Now look at the bottom. If your alpha is way too big, you can literally jump clear over the lowest point and end up even higher on the other side. You just risk bouncing back and forth, getting nowhere.
So you can see it's this incredibly delicate balance. Picking the right alpha is pretty much the difference between slowly but surely getting to the right answer and just completely failing to find it at all. Okay, but this brings up a really interesting thought. What happens if we actually make it to the bottom of the hill? You know, we land in one of those little valleys, a local minimum. What does the algorithm do then? Does it just keep trying to take steps?
Well, think about it. When you're at the very bottom of a bowl, the ground underneath your feet is perfectly flat, right? The slope is 0, which means our derivative is 0.
And if that derivative term is 0, well, look at the formula. It's our current position minus nothing. Alpha times 0 is 0. The whole update part just vanishes. Our position doesn't change. And that's exactly what we want, right? We've arrived. The algorithm just stops. Mission accomplished.
This brings us to the grand finale. And honestly, this is my favorite part. It's the most elegant, most brilliant feature of this whole thing, the automatic convergence.
Just look at this graph for a second. As we get closer and closer to that minimum point, what happens to the slope? It naturally gets less steep, right? It starts to flatten out. And remember, a flatter slope means a smaller derivative. And since our step size is the learning rate times that derivative, our steps automatically start getting smaller and smaller. No extra work needed.
So let's just walk through that logic one more time because it's so cool. As you get closer to the bottom, the slope gets flatter.
That makes the derivative term smaller, and because the derivative is smaller, your update step automatically gets shorter. It's this beautiful self-regulating system.
And that right there is the big takeaway. You don't need to mess with alpha. You don't have to write some fancy code to decrease your step size over time. The algorithm does it all by itself. It naturally takes big steps when it's far away and tiny, careful steps when it's close. It's just a really elegant piece of design.
And there you have it. The code is cracked. Gradient descent is really just a clever way of using the slope to tell us where to go and a learning rate to decide how fast to get there, all with this amazing built-in feature that automatically slows things down at the end. So the big question I want to leave you with is this. Now that you know how to find the lowest point of, well, almost any function, what powerful problems are you going to solve with it?